Okay, so let's continue with our chapter of capacitor. So in this subtopic, we are going to talk about the capacitor in series and parallel circuits. So since the capacitor is an electric component, so it eventually will be attached to the circuit. So this is capacitors in series and parallel circuits. Oops, parallel circuits. So since the capacitor is attached to the circuit, so it means that capacitor is actually attached to the power supply. So in this form, the capacitor is actually in the form of the charge capacitor instead of isolated charge capacitor. Okay, so the what I mean for the charge capacitor is actually the capacitor that is connected to the battery. So that's the difference. Okay, so this is the topics. So let's begin with the capacitor in series circuits. Capacitors in series circuits. So before that, we need to observe what is the diagram that we have. So we know that if the capacitor is arranged in series, so this will be the structure of the arrangement of the capacitor. So assume I have a 3 capacitor which arranged in the circuit, which arranged in series circuits. So in series circuits, we know that the potential difference across the series circuits is actually Vt is actually equals to V1 plus V2 plus V3. So this V1, V2, V3 is the potential difference which across the plates of these 3 capacitors. So this is the equation for the potential difference, the total potential difference in series circuits. As for the charges, so the charges is actually follows the rules of the current. So my charges, the total charges which exerted by the capacitor is actually equals to Q1 equals to Q2 and equals to Q3. Okay, so we know that my Q is actually equals to CV. Okay, so if I express the V in terms of Q over C, so what I have for this one is if I continue this equation, so what I have is actually Q over CT is equal to Q over C1 plus Q over C2 plus Q over C3. So I didn't write the Q as Q1, Q2, and Q3 since all the charge exerted in the capacitor are the same. So if I factorize this Q out of the equation, so what I get is 1 over C1 plus 1 over C2 plus 1 over C3. So this is Q over CT. So if both Q are cancel each other, so finally, so I just write it here since there's insufficient space. So finally, the total capacitance exerted in the series circuit is actually 1 over C1 plus 1 over C2 and finally plus 1 over C3. So this is the final answer. Okay, so this is the principle for the series circuits. So let's just move on to the second principle, or the second whatever, the second knowledge, which is the capacitor in parallel circuits. The capacitors in parallel circuits. So before that, we need to know what is the rules that exerted by the potential difference and the electrical charges in parallel circuits. So in parallel circuits, we know that the potential difference which across the capacitor or across the whole circuits is actually equals to the total potential difference is equal to the total potential difference across the first capacitor plus equals to the potential difference across the second capacitor, and same goes to the third capacitor. So the diagram should be in this form. Okay, so this is actually a simple diagram. So let's say this circuit is actually connected to a battery, since it is a charged circuit, a charged capacitor instead of charged isolated capacitor. Okay, so this is the rules for potential difference. So what about the electrical charges? So the electrical charges in parallel circuits, which follows the rules of the current. So this Q is actually equals to the Q1 plus Q2 and plus Q3. Okay, so since our Q is equal to CV, so what I have here is actually equals to the C1V plus C2V plus C3V. So I didn't write this V as V1, V2, and V3, since all of them are the same. So this is the CTV, of course. So what if the V can be cancelled by the both sides? So what I get for the final equation is actually equals to the CT, the total capacitance in the circuit, is actually equals to the C1 plus C2 and finally plus C3. So this is the principles for the total capacitance which exerted in parallel circuits. Okay, so alright, so we've done for the properties of the capacitors, which in the two situation, which is in series form or the parallel form. Okay, so let's look out for some examples for the calculation of the total capacitance in some different circuits. Okay, so the example I have taken is the mixture of the parallel circuits and the series circuits. So for the first example, so let's say this is my circuit, and okay, this is my first capacitor, second capacitor, and this is the third, and finally this is the fourth capacitor. So obviously this fourth capacitor is actually in parallel, and these two capacitors are actually, let me explain later. So let me just draw it down. So this is the fifth capacitor. So assume this is the C1. So my C1 has the 5 mil farad. So SI unit for the capacitor and the capacitance of the capacitor is actually in farad. So farad is actually in the spell as F-A-R-A-D. So this is the SI unit for the capacitance. Okay, so this is not the main point. Okay, so for the second capacitor is also 5 farad as well. As for the third capacitor, my third capacitor will be 8 mil farad. And this same goes to the fourth capacitor, 8 mil farad as well. So as for the C5, is actually 20 mil farad. So our main objective is actually find out the total capacitance which exerted in this circuits. Alright, so let's count it step by step. Okay, so let's begin with the first and the second capacitor. So we can see that the first and the second capacitor and the third, and same goes to the third and the fourth capacitor, both of them are actually arranged in series. And as for the, if we combine the 1, 2, 3, 4, the 4 capacitor, so this C1 and C2 is actually parallel to C3 and C4. So before that, let us find the total capacitance for C1 and C2. So since C1 and C2 is in series form, so my total capacitance 1 over CT is actually equals to, so this is the first total capacitance, so I prefer to write it as CT1. So this is 1 over C1 plus 1 over C2. So this is 1 over 5 plus 1 over 5. So this mu is not necessary for us to write because the final answer that we write is actually in terms of mil farad. So this is 1 over CT. So what I get for the 1 over CT1, okay, so let me just count it down. 1 over 5 plus 1 over 5. So what I get for the CT1 is actually 2.5 mil farad. Okay, so after counting the CT1, so let's move on to the CT2, which is the total capacitance for the third capacitor and the fourth capacitor. So my CT2 is equal to the 1 over C3 plus 1 over C4. So I just continue here. So my CT2, 1 over CT2 is equal to 1 over C3. The C3 is 8 plus 1 over 8. So my CT2 finally is 4.00 mil farad. So this is the CT2. So since the CT1 and the CT2 are parallel to each other, so finally my CT3 is equal to my CT1 plus my CT2. So what I get for the total capacitance in this parallel circuits, so it's actually equals to the 2.5 plus 4.00. Okay, so what I get for the CT3 is actually 6.50 mil farad. So this is C3. So after counting the C3, which is the whole parallel circuits, the capacitance for the whole parallel circuits, so we are about to combine this CT3 with the C5. So since the CT3 and the C5 is counted as series arranged in series to each other. So finally my CT4 is actually equals to 1 over CT3 plus 1 over C5. So my CT3 is actually 1 over 6.5 plus 1 over 20. So this is CT4. So finally my CT4 will be 1 over 6.5 plus 1 over 20. So my final answer should be 4.906 mil farad. So this is how we find the total capacitance in a circuit. Okay, so let's move on to the second example for the calculation of the total capacitance in a circuit. Okay, let me just erase this one. So this example, the next example is actually quite, should I say, quite complicated. So, okay, let me just draw it down. Okay, so this is the one of the capacitor, and this is the second capacitor, and this is the third capacitor, and this is the fourth capacitor. And at the middle of this circuit, there's actually one capacitor which is inclined to all the fourth capacitor. Not inclined, and should I say, not arranged with the same position of all capacitor. So the circuit is actually in this form. Okay. Okay, so come on. Oops. Okay. So the middle of this capacitor is actually in this form, which is quite confusing. So in this section, and this section is actually attached to another wire. So there's nothing at the end of this wire. Okay. So assume that this will be my C1. So my C1 is actually 20 farad, mil farad, sorry. So my C2 should be 80 mil farad. As for my C3, so my C3 is the middle one. So this is the 14 mil farad. So my C4 is actually equals to 120 farad, mil farad. So my C5 is actually equals to 48 mil farad. So my main objective is actually, of course, find out the total capacitance in this circuit. So before that, we need to observe which capacitors are actually in series and which capacitor are actually in parallel. So before that, let us look out for the first and the second capacitor. So obviously this C1 and this C2 are actually series to each other. Series. So after, okay, so this C1 and C2 are series to each other. So if we combine C1 and C2, and we can see that this C1 and C2, the combination of C1 and C2 are actually parallel to C3 in this middle one, this middle capacitor. So after moving to this C3, after calculating the combination of C1 and C2 and C3, which is parallel to each other, so we need to find out the combination of, okay, so let us just do step by steps, so that I more easier to explain. So for the first one, of course, which is series, so my CT1 is equal to 1 over 20 plus 1 over 80. So my CT1 is equal to, so my CT1 is actually 16 mu farad. So this is my CT1. So the CT1 is actually the combination of C1 and C2. So the total capacitance with C3, so since both of them are parallel, so my CT2 is equal to my CT1 plus the C3. So assume that they are parallel. Not assume, it's uh, actually is in the form of parallel. So my CT1, remember, is actually the combination of the first and the second capacitor. So my 16 plus the 14, so what I get is actually 30 mu farad. So after that, after calculating the CT2, so let's just move on to the CT4. So this CT4 with C3 is actually in parallel, since not parallel, sorry. So this the combination of C1, C2, and C3. So this combination of C1, C2, and C3, which is CT2, are actually series to the fourth capacitor. So series, the formula should be the 1 over CT3 equals to 1 over CT2 plus 1 over C4. So this is 1 over 30 plus 1 over 120. So what I get for the CT3 is equal to 1 over 30 plus 1 over 120. So what I get is actually 24 mu farad. So we have done for this C1, C2, C3, and C4. So finally we have came to C5. So some of you might consider the C4 and the combination of this C1, C2, C3, and C4 are actually series to C5 due to this path C4 that is directly to C5. But in fact, the concept is actually wrong. This is because the C4, after moving this path, there's actually another path which is connected to this way. So this same goes to this part. There are another way besides going to C5. So I can assume that my CT3, which is the combination of the capacitor from 1 to 4 capacitor, so I can conclude that my CT3 is actually parallel to C5. So my CT4 is actually equals to the CT3 plus C5. So 24 plus 48 is actually 72 mu farad. So I repeat again. So this, I believe there is no problem for this one. So the problem is actually to find out the total capacitance of this CT3 and C5. So I repeat again, and basically we know that this CT3, which is the combination of C1, C2, C3 and C4, is actually should be series to C5, but in fact there is another way which connected there's another wire which is connected to the other ways beside the C5. So this in this point there are two ways, and in this point there's actually three ways. So regardless of this point, so we focus on this point. So this point consists of two ways. So these two ways tell us that the CT3 is actually parallel to C5. So that is why I use the formula for the the formula of the parallel circuits, which is CT3 plus C5. So finally what I get is actually 72 mu farad. Alright, so we have done for the example. Okay, so let's move on to the new subtopics. Okay, so for the next coming subtopics, we are going to discuss about the energy stored in a charged capacitor or the energy stored in a charged isolated capacitor. So before that, there's nothing need to memorize. Okay, let me just see it for a while. Okay, so for the first part, let us discuss about the energy stored in a charged capacitor. So basically, the charge capacitor is defined as the capacitor which is connected to the circuit. Okay, so we know that capacitor is actually used to store the electrical charges. So this electrical charges is actually exists in the form of electrical energy. So this electrical energy, we actually call it as electrical potential energy. Potential energy. So this electrical potential energy has the symbol which is U. So my U is actually equals to the half CV square. So this is the main formula. So we know that Q is actually equals to CV. So what I have here is actually equals to QV. And this is U, of course. So this is the one of the two of the electrical potential energy. So that's another formula. So let's say this is the expression for the potential difference across the two plates of the capacitor. So V is actually equals to Q over C. So what if I substitute this 1 over 2 CV squared? So my V is actually Q over C, and this is okay, and what I get is actually the Q squared over C. Alright, so this will be our third formula. So these three formulas consist of their own relation respectively. So for the first one, okay, so let me just erase all this one first. So the derivation of each formula has their own main objective. So let me show you this. Okay, so from the U, for the first one, U is actually equals to the half CV squared. So I can see that my U, the electrical potential energy, is actually directly proportional to the potential difference, the square of potential difference across the two plates of the capacitor. So in this case, the capacitance of the capacitor are actually constant. So assume the capacitor, the space between the two plates are free space, so there's no dielectric. So this capacitance are actually constant. So the variables that is actually changing is actually the electrical potential energy and the potential difference. So I can say that U is directly proportional to the square of the potential difference. So what I get for the graph of electrical potential energy against the square of potential difference. So what I have here is actually a straight line. Okay, so as for the second formula, so this is the Q square over 2C. So, okay, so to be reminded that the gradient of this curve, is actually equals to the C over 2 due to this U and this V square is a variable, so this C over 2 is the gradient. So as for this one, so this formula consists of U, Q square, and C instead, and there's no potential difference in this formula. So I can say that since C is my constant, so since this one is a constant, and hence my U is actually directly proportional to the square of electrical charges. So it means that if the electrical charges, magnitude of the electrical charges exerted on the two plates increases, and hence the electrical potential energy across the two plates are also increased. Okay, so if the graph, what I have here is actually U, and this is Q square, and this one should be my straight line graph. So my gradient is actually equals to 1 over 2C. Okay, so this is the charge capacitor, the principle for charge capacitor. Okay, so we have done for energy stored in a charge capacitor. So let's just move on to the energy stored in a charge isolated capacitor. So let me just erase this one. So charge Okay, let me just erase this one. And this, in this case, is actually in a charge isolated capacitor. Okay, so let me see what is the first one. So for the charge isolated capacitor, so this isolated capacitor, we know that the capacitor is actually not connected to the circuit or connected to a battery. So in this case, let me just erase this one. So in this case, my electrical charges, which is Q, are actually constant. Okay, so since my Q is a constant variable, so the formula that I use to find out the relation of the energy stored with the other variables is actually equals to the U equals to Q squared divided by 2C. So the variables that is actually changing in this is this one. So the electrical potential energy, the changes of electrical potential energy is due to the changes in the capacitance of the capacitor. So this, if we are allowed to the if we are going to allow the capacitance to changes, so this capacitance, the changes of the capacitance of the capacitor is actually due to several factors. So remember that from the previous part, we did talk about the formula for the capacitance of the capacitor. So this is the main formula, which is epsilon naught A divided by D. So from this formula, there is actually two factors that will influence the capacitance of the capacitor. So the first one is actually this one, and this will be the second one. So for the first one, it's actually the surface area of the plate, of course. Surface area of the plate. And for the second one, is actually the plate separation. Which will influence the capacitance of the capacitor as well. So there's another one which we taught from the previous video, which is inserting dielectric. So the inserting dielectric. So inserting the dielectric will also influence the capacitance of the capacitor. Okay, so let's move on to the okay, let me just erase this one. So let's discuss one by one. For the first one is actually the surface area of the plates. Okay, let me just erase this one. Okay. Alright, okay. So for the first one, we're going to talk about the increasing the plate separation first. Okay, so increasing the plate separation. So the plate separation is actually denoted as D. So from the formula of the capacitance, if the split separation is about to increase, and hence the capacitance of the capacitor will be decreased. So from the energy stored, U is actually equals to the Q square over 2C. So if the capacitance of the capacitor decreases, hence the energy stored will be increased. So that's actually the reason why the energy store increase. So assume that this is my capacitor. If there's an attractive force, so there's external work done. So this is my external work done, or we can say that this is actually the external force. So all the work done, all the work done. So the external force is actually applied to separate the two attractive plates further apart. So okay, let me just observe for a while. So this external work done is used to separate the two plates further apart. So this mechanical energy, so this work done is actually known as the mechanical energy. Mechanical energy. So this mechanical energy is actually the external work done, which is used to separate the two plates of the capacitor. So this mechanical energy is after pulling the two plates further apart. So this mechanical energy is actually converted to electrical energy. After two plates are being pulling further apart, so this work done is converted to electrical potential energy. So that is why our electrical potential energy increase due to the external work is done on the capacitor to move the plates further apart. Okay, so this is the first concept, first factor. Okay, so I repeat again. Okay, so we can see that from the formula, if the plate separation is increased, the capacitance of the capacitor will decrease. So the decrease in the capacitance of the capacitor will causes the electrical potential energy to increase. So in so this is because the reason why is because um, the external force, or should we say the mechanical energy, which is used to pull the plates of the capacitor further apart, is actually converted to electrical energy. So this actually shows that my energy is conserved, and the energy is conserved and there's no energy lost to the surroundings. Okay, so we have done for the first one. Alright, so let's move on to the second one. So this second one, we're going to discuss about the inserting dielectric. Okay, inserting dielectric. So this inserting dielectric, so we know that the capacitance of the capacitor will increase. Capacitance of the capacitor will basically increase. So the reason for the capacitor increase, we have already discussed from the previous video. So this is due to the decrease in electric field strength, and hence the potential difference across the plates will decrease, and hence the capacitance will increase. So based on the formula, U is actually equals to the Q square divided by 2C. So increase in capacitor will causes the electrical potential energy to decrease. So why? This is because the attractive, okay, so let me just draw it down. Okay, so let me just observe for a while. Okay, so let me just draw it more bigger. Okay, so assume that this is my capacitor. So assume that the dielectric is actually fill the space between the two plates. So this will be my dielectric. So in this case, there is actually the attractive force. Okay, let me just use another color. So there's actually an attractive force between the dielectric and the two plates. So this attractive force, so this attractive force. So this attractive force is actually used to pull the dielectric to these two plates. So let's say this dielectric is being pulled to the left side of the first plate, and this dielectric is also being pulled by the second plate. So this pulling force, we can say that is the we can say that the work is done to pull, okay, there must be a subject. Work is done by the capacitor, by the capacitor. Work is done by the capacitor. Okay, so let me just observe for a while. To attract. Okay, let me just, okay, I just write here. So work is done by the capacitor to attract the dielectric dielectric okay, and the two plates. So is it correct for the sentence? Okay, so let me just rewrite again. So the decrease in energy is due to the attractive between the plates of the capacitor and the dielectric. So as I said just now, the work is used by the capacitor to attract, or we can say that pull the dielectric, so that they are attractive. Or how should I describe this? So as long as the energy is used to attract the dielectric, which is lies between the two plates. Okay, so yeah, this is the concept and the reason why the energy is decreased. This is due to the attractive between the plates of the capacitor and the dielectrics. So we have done for the second factor. So let's move on to the third factor, which is the surface area, if I'm not mistaken. Okay, so increasing the area, increasing surface area. So we know that the capacitance is actually equals to the epsilon naught A over D. So if the surface area is increased and hence the capacitance of the capacitor will also increase. So based on the electrical potential energy, increase in the capacitance will decrease the electrical potential energy. So in this case, my U will decrease. So in fact, this is because work is actually done by the capacitor to pull the two plates to increase the plate's area. So work is done. So work is actually done by the capacitor to pull. Okay, so let me just observe for a while. So, okay. Alright, so let me just observe for a moment. So I think there's some mistakes here. So, okay. So where is it? Okay. So is it a mistake here? Effective area. Pull the two plates. Yeah, I think this is correct. So work is actually done by the capacitor to pull the plates in order to increase the plate's area. Okay, so to pull the plates in order to increase the plate area. So work is actually done to increase the surface area of the plates, and hence the electrical potential energy on the capacitor will actually decrease. So this is the third reason. So let's move on to another additional parts in this subtopics. So just now we actually discussed the inserting dielectric in an isolated capacitor. So in this case, we are going to talk about what will happen to the energy stored if the dielectric is inserted in a charged capacitor, which is connected to the circuits. Okay, so inserting dielectric into a charged capacitor. So this charge capacitor is connected to a battery or the circuits. So initially, okay, so let's say I have my capacitor. So this is actually the power supply. So initially, if before inserting the dielectric, so the potential difference across the two plates of the capacitor. So initially my V naught is actually the equals to the E. So this E is actually the meant by the electromotive force. So this E is actually equals to the potential difference which contained inside this battery. So hence the potential difference exerted by the capacitor is actually E. Okay, so after inserting dielectric, so we know that after inserting dielectric, so the polarization of the dielectric molecules will produce the reverse electric field strength. So the electric field strength, the resultant electric field strength will decrease, and hence, so the electric field strength will decrease, and hence my uh, my potential difference across the two plates will also decrease. So I can conclude that finally the potential difference, okay, so the potential difference across the two plates decreases from E to V. Okay, so when the potential difference across the two plates decrease to this V, so when the potential difference decrease, so this battery is actually will tends to charge the capacitor. So for the third statement, the battery or the power supply, we can say as power supply, will charge the capacitor. So when charging the capacitor at the same time, so my electrical charges which exerted by the two plates, which is Q, will start to increase. So my electrical charges which lies on the surface of the two plates will actually increase. So my electrical charges increase until the potential difference back to, okay, let me just write down. So my electrical charges will increase until the V return to E. So until the potential difference is equal to the electromotive force. Okay, so in this case, okay, let me just erase this one, erase it all. Alright, so I'll erase this one as well. So in this case, I can say that my V is actually constant. So my V is actually equals to electromotive force. So although the V is actually varies due to the dielectric is inserted, but the final potential difference that we obtain is actually this electromotive force. So I can say that my potential difference across the two plates is actually constant. So the one that is actually varying is actually equals to Q is equal to CV. So we know that this one is the constant. Sorry. Okay. So this one is actually constant. So the variables that is actually varying is actually this one, electrical charges and the capacitance. So the Q is actually varying is due to the when the battery is charging the capacitor. So hence the electrical charges, the magnitude for the electrical charges which lies on the surface of the two plates will increase. So as for the increase in capacitance is due to the dielectric is inserted between the two plates. So okay, so from the formula, which is half CV square, CV square, or U is actually equals to half QV. So since this V, both V is actually constant, so the variables is actually this one, the manipulated variable is this one. So this is the responding variable. So this is the responding variable as well. So in this case, we know that the capacitance of the capacitor will increase. So let me just use another color. So in this case, the capacitance of the capacitor increase, and hence my U is actually increased. So the electrical potential energy will increase. So as for this formula, so when charging the capacitor at the same time, the magnitude of the electrical charges will increase. So this one will increase, and hence the electrical potential energy will also increase. So this is how we determine the electrical potential energy due to the factor that is affected. How should I inscribe this one? So the electrical potential energy is due to the increase in capacitance of the capacitor and the electrical charges which exerted on the surface of the two plates. Okay, so both C and Q is actually the manipulated variable which is changing. So if this both manipulated variables increases, and hence the responding variable, sorry, which is the electrical potential energy, will also increase. So to be note that this is actually a charged capacitor and not the charged isolated capacitor. So that's the difference. So I hope you understand about the concept as I explained just now. So I think we'll stop here now, and I'll see you in the next video. So if there is any question need to be asked, and please comment below this video. So I'll see you next time. Thank you. Bye.